it is time, and we can see that there are some people still joining. In the meantime, we have one more minute left. I would like to ask any one of you if you have any questions regarding our previous discussions on anything on evaporation or humidification or equilibrium stage processes. So maybe you have some time so that if you have any questions, you can ask, and I will try to answer your questions. Do we have any question? Yesterday, I had received one question around a certain calculation in the recommended problem A1 in the evaporation. So I have corrected. There was a little mistake, so I have corrected, and I put the new solution in the canvas, so you may watch it. And there was also a question around the conversion of 102 millimeter of mercury in that particular problem. So for if you have 102 millimeter of mercury as an absolute pressure, then you can calculate for from the appendix number 7, which gives us information from the Fahrenheit and also in the pound per square inch psi. So you can convert 102 millimeter of mercury into pound per square inch. So I think it was 1.9 something, and then you can calculate the latent heat of vaporization at that temperature. So it's like simple conversion. Maybe you can use the appendix number 7 from the book, or if you would like to use any steam tables in any unit, either in the SI unit or in British units, whatever you feel easy. There are so many different types of steam charts or steam tables are available, and also tables for properties of the liquid and properties of the gases. So it's up to you that what kind of table you would like to use. And there was a couple of questions around the examination. There was one question that if you are allowed to resubmit your assignment if it is not correct. So I had a discussion with Jorgen yesterday, and I think it was the same. So if you submit your assignment for a particular separation technology into the canvas within the deadline, so your points will be based on your first submission. But in case if your submission is not correct, if your answer or solution is not correct, we will give you an opportunity to resubmit. But the resubmission will only help you in passing the course. So maybe even if you have done it right, you can only get 3 grades. You will not get high grades. So the main grading will be based on your first submission. The resubmission will be allowed if your submission is not correct, but it will only help you in order to pass the course or pass that particular assignment. The assignments that you have been submitting from Jorgen part and for my part in the upcoming days, all the points that you get from each assignment, it will be added together in order to finalize your final grades. Let's say if we have 100 points in all assignments, let's say like at the sum of the points in all assignments is 100 points. So in order to get grade number 5, you need to have more than 85 points. In order to get grade 4, then you need to have total points more than 75, like 75 or more than 75. And in order to pass this course, you must have points more than or equal to 65. So this is the way that your grading will be done. And so resubmission will be allowed, but your main grading will be done on the basis of your first submission within the deadline. If you submit your assignment after the deadline, you can still do it, but your grades will be affected. You will not get full grades even you if you have done your assignment correctly. This is what I have already informed you at the beginning of this course. So it's very important that try to submit your assignments in time, right? So before I start my discussion on distillation, I would like to ask you that if any one of you have any question around the examination, or if any clarification is needed. All right, then I'll move to our discussion on distillation. This is one of the I would say the most favorite topic of mine. I have been doing a lot of my work around distillation. I did my internship in an oil refinery, and I was working around 6 to 8 weeks with distillation column, and these large and huge distillation columns are some sort of a fantasy for many chemical engineers because you learn a lot when you are working with distillation columns, because normally they are considered to be the heart of the oil refinery, and they can also be considered as the most important organ of petrochemical industry. So this distillation is a very important equipment for process engineers, for chemical engineer, for operational engineers, right? So it's very important for you to learn about the basics of distillation, how distillation works, how we calculate the number of ideal stages, number of ideal plates, how different plates look like, what happen at each stage or each plate, right? So we have distillation for binary system when there are only two components are involved in the mixture. But in many or most of the applications in chemical process industry, we might be dealing with a mixture like crude oil. So the crude oil contains many dozens of different types of components inside the crude oil. So we use distillation in order to separate those components on the basis of their boiling points, or on the basis of their volatilities, right? So we can produce naphtha, like which is gasoline, kerosene oil, jet fuels, oil for home use, gas oils, lubricants, fuel oils. So paraffin waxes, like the candles that we use in our daily life. So so many different types of components that we can produce from distillation of crude oil. So I will go into the detail about distillation, how we do the distillation, how we can calculate the number of stages and ideal plates. So the main learning outcomes from this discussion will be we will develop our understanding of distillation and relative volatility, how we can use vapor liquid diagram, this VLE diagram, which is very important. I will very briefly discuss the flash distillation of binary mixtures or single stage distillation. We can perform material balances in plate columns, and the most important part in distillation, how we can estimate or calculate number of ideal stages or number of ideal plates. And there is a very famous or a popular method in order to estimate the number of ideal plates, which is called McCabe-Thiele method. So I will show you step by step that how you can calculate the number of ideal stages. So let's start with distillation. Distillation is a very complex uh, process in terms of operation, but in reality, by definition, it is a very simplified version of separation on the basis of boiling points of individual components, right? So we do the separation of components of a liquid mixture, and we separate them on the basis of their difference in boiling point or differences in their volatility, right? And normally the distribution of components will be between liquid and gas phase in the mixture. The distillation process depends mainly on the vapor pressure characteristics of liquid mixtures, which is some sort of the description of the volatility or the relative volatility. So the relative volatility is very important. The relative volatility gives us information about the differences in the volatility between two components or more components. And this is also reflected in terms of their boiling points. And this is also a measure of how easy or how difficult a separation will look like, right? So relative volatility helps us in indicating how easy or difficult a particular separation will be. since we know that relative volatility is dependent on the partial pressures or the volatility of individual components, so we can also write relative volatility in terms of their fractions in the vapor phase and in the in the liquid phase, and we can also write the relative volatility of two components in terms of partial pressures. So partial pressure with their mole fraction in the liquid phase, and partial pressure of any different component like Pa or Pb with respect to their mole fractions. This chart is just to show you that how there are different optimal relative volatilities for many different types of binary mixtures. So if you look at the first mixture, which could be the mixture of benzene and toluene. So benzene is a component which is more volatile. It means it will have a less boiling point than the other component. So if you see, the benzene has a boiling point of 80.1 degrees C. And if we have a mixture of benzene together with toluene, so benzene will be the more volatile component and toluene will be the less volatile component. And the toluene will have a normal boiling point of 110 degrees C, right? So there is a difference between their boiling point. So if we heat up this kind of a solution that contains benzene and toluene, benzene will have a tendency to evaporate or to boil at a low temperature like 80 or 85 or 90 degrees C as compared to the toluene. Toluene will still evaporate, still vaporize at those temperature, but the concentration of benzene in the vapor phase will be much higher than the concentration of toluene in the vapor phase. And similarly, in the liquid phase, the concentration of toluene will be higher as compared to the concentration of benzene. And this is how we do in different stages, and we keep on increasing the concentration of benzene in the vapor phase, and we keep on increasing the concentration of toluene in the liquid phase. So if you look at their optimal relative volatility, so it is like, let's say, 2.34. So it means it has a good tendency of separation. Separation will be not difficult. But if you take an example of M-xylene with P-xylene, so M-xylene has a boiling point of 139 degrees C, and P-xylene has a boiling point of 138 degrees C. So the temperature difference is not that big. They are very close to each other, just a difference of zero point 0.8 degrees C, which is not that big. And they have a quite similar volatility. So their relative volatility is around 1.02. So it means if we have a mixture of M-xylene or P-xylene, it will be very difficult to separate them using simple kind of distillation. Then we might need to use different types of distillation, like the distillation that we can do in vacuum, or we can add one component into the distillation so that it can increase or decrease the boiling point of one of the component in order to increase the volatility difference, right? So when we have a relative volatility close to one, it means the difference is very small, and it means the separation will be very difficult. And if we move away from one, so if we keep on increasing the relative volatility more than one, like let's say 7, 5, 6, so these type of components will be much more easy to separate through normal distillation. So this is just to show you the optimal relative volatility of some of the most common mixtures in the oil refineries and also in the petrochemical industry. Now I would like to show you a very important diagram, which is called vapor liquid diagram. This vapor liquid diagram gives us information about mole fraction of a certain component in the liquid phase and its relationship with the mole fraction of that component in the vapor phase when they are in equilibrium. This picture is an equilibrium diagram for benzene toluene mixture at 1 atmospheric pressure, right? So normally we calculate or we know the data for the equilibrium from experiments. So we do experiments and we calculate at what conditions the mole fraction of benzene in liquid will have a certain value for mole fraction of benzene in the vapor phase. So normally equilibrium data is given by the experiments. So when you do problem in your assignment, so you will be given with equilibrium data, right? And then I will show you that how you can calculate the number of stages later. right? So this is a vapor liquid diagram, a relationship between the mole fraction of one component in the liquid phase with the mole fraction of that component in the vapor phase. And if you look at this picture here, you can see that the equilibrium curve is quite consistent. It's not moving around. It's very consistent throughout the mole fraction of benzene from 0 to 1. But there are many different systems or many mixtures. They do not have a consistent vapor liquid curve, and we can call them as vapor liquid curve, equilibrium curve for non-ideal systems, right? But we also have certain systems where we achieve a point which is called azeotropic point, when the mole fraction of one component in the liquid phase becomes equal to the mole fraction of that component in the vapor phase. So for example, if there is, like, let's say, zero point 0.5 is the mole fraction of the component in the liquid phase, it will be zero point 0.5 in the vapor phase. So it means there is no gradient is available. There is no driving forces available for the mass transfer, right? And normally these points are called azeotropic point. And those kind of solution, we call them azeotropic solutions, right? In this, there are some methods that how we can do the distillation for azeotropic solutions or azeotropic mixtures. But in this course, we are not going into the details about azeotropic point or azeotropic distillation. Now I will start with flash distillation. This is just to show you a single stage continuous distillation column where a liquid mixture is partially vaporized. So we add our feed into the system and we increase the temperature and we allow the separation based on the vapor and the liquid phase. And then we can very easily do the material balance around this kind of system. So let's say if the feed is 1 mole that is entering into the flash distillation column, and we can consider xf is the mole fraction of like one component in the feed, and we can call the distillate or the overhead product, the floor is f, and yd is the mole fraction in the vapor phase. And by just doing the balance, so it's 1 here and f, so it means 1 minus f will be the flow that is going in terms of the liquid, and we can call xb, so it will be the mole fraction in the liquid phase. So when we rearrange it in terms of the mole fraction of that component in the vapor phase, so we will have this kind of an equation. And this equation will helps us in order to find the slope of operating line. So 1 minus f over f will be the slope of the operating line, and xf over f will be the intercept. Similarly, you can perform a very simple energy balances. So you need to consider the enthalpies of the vapor and the liquid that are leaving the flash chamber. So similarly, you will have HF will be the enthalpy of the feed, HY will be the enthalpy of the vapor, and HX will be the enthalpy of the liquid product. And this is the flow of the system. So 1 minus F is going in the liquid phase, F is in the vapor phase, and 1 is the flow of the feed, right? So you can perform a very simple material and energy balance around a flash distillation of binary mixture. You can also show the graphical presentation of flash distillation. So similarly, if we have a vapor liquid equilibrium diagram for benzene, right? So on the x-axis, we will have mole fraction of benzene in the liquid phase, and on the y-axis, we will have mole fraction of benzene in the vapor phase, and we can draw an equilibrium diagram or equilibrium curve, right? So if we know the value of f, like, and we know the xf, which is the mole fraction of that component in the liquid phase. So we start from xf, we go till the diagonal line, and then we have to consider what should be the slope of the line. So slope of the line will be 1 minus f over f, and it's minus, so it means it's on the other side of the 90-degree diagram, right? And then we have to think about what would be the quality of the feed, right? And you also need to consider what will be the mole fraction of particular component. Let's say mole fraction of benzene in the liquid phase, and at equilibrium it will have a mole fraction of benzene in the vapor phase. And it's very important to learn about that how you can draw the line for the feed quality. So the feed quality normally that we use in distillation, there are three ways that how we see the quality of the feed. The feed can be 100% liquid, so we can call it as saturated liquid. So there is no vapor coming with the feed, so it's only the liquid phase of the feed. There is other way that if you have 100% of vaporization of the feed, so it's only vapors that are entering into the distillation column, and there could be a mixture of liquid and vapors in the feed, right? So when you need to draw the feed line, there will be a vertical line if there is no vaporization. So if the liquid is saturated, if the feed is saturated liquid, and the feed line will be horizontal if it is 100% vapors or 100% complete vaporization. And if it is a mixture of vapor and liquid, then the operating line for the feed, it will be in between these two systems, in these two lines. Now I will show you a system for multi-stage continuous distillation column. So if we see an action on ideal plate, what happens? So there will be two streams that will be entering into the plate end. So one is the vapor stream that is entering to the plate end, and there is one liquid stream that is going to be enter the plate end. So the vapor will be entering from plate n plus one, so we can call it Vn plus one, and the mole fraction of that component or more volatile component in the vapor phase, we denote it as Yn plus one, right? So they are coming with Yn plus one mole fraction, and the liquid is entering with a mole fraction of Xn minus one. So from the boiling point diagram that shows the rectifying section in the ideal plate, the the mole fraction of that component or a more volatile component in the vapor phase will increase from Yn plus 1 to Yn. So it will increase. And what will happen for the mole fraction of that component in the liquid phase? So Xn will be higher than Xn. So its mole fraction will keep on decreasing from Xn minus 1 to Xn. So this is how the mole fractions for a particular component will increase when we move upward in terms of vapors, and the mole fraction of that component in the liquid phase will keep on decreasing if we follow the route of the liquid stream. So this is just to show you that when they enter, when this stream and this stream enters, they are not in equilibrium, because if they are in equilibrium, there will be no driving force for the mass transfer. So the driving force should always be there in order to have a mass transfer. So Vn plus 1 and Ln minus 1, they should not be in equilibrium. But for an ideal stage, for an ideal plate, it is important that the streams which are leaving a particular stage or the stream which are leaving the particular plate, so they should be in equilibrium. So it means Vn will be in equilibrium with Ln. The mole fraction of that more volatile component in the vapor phase will be in equilibrium with the mole fraction in the liquid phase. So the leaving stream for an ideal stage, they will be in equilibrium, but the streams which are entering a particular stage or a particular plate, they should not be in an equilibrium so that we can have a mass transfer. I would like to ask you that if anyone have any questions around how we achieve the mass transfer and equilibrium on a particular plate. Do we have any questions? All right, then I'll move on. And this is just to show you a continuous column with rectifying and stripping section. So normally what we do that when we enter our feed into the distillation column, the section which is above the feed plate or feed stage, it is called the rectifying section. And the section of the distillation column which is below the feed plate or feed stage, it is called stripping section. So what happens in the distillation column, the vapors move upwards and the liquid moves downwards. And we have the vapors with containing more volatile component. we add that vapor to the condenser, and the vapor are condensed in order to produce liquid. Some of the liquid is taken out as an overhead product, but some of the material is taken back into the distillation column, and we call it as reflux. And the ratio of the amount of liquid that we return back to the distillation column with the overhead product is called the reflux ratio. And if I remember, I mentioned this reflux, that why we need to have reflux in the distillation column, because if we do not add the liquid back into the distillation column, these stages which are in the rectifying section, they will dry, because all the vapors, they will be taken out from the distillation column, and we will have a dry plate, and there will be no mixing between the liquid and the vapor phase, and there will be no mass transfer. So we normally send part of the liquid back to the distillation column in order to keep the liquid level inside the distillation column, and also to increase the purity of the vapors or purity of the overhead product. So this is normally what we do, and we use reflux pump to return the liquid back to the distillation column. And so, as I mentioned, reflux provides downflowing liquid that is needed to act on a flowing vapors. Now, how we can perform the material balances in the plate columns? So let's say if we have a feed that has a flow of F, and D is the amount of the distillate, and B is the amount of the bottom product, and XF is the, let's say if we are taking in terms of more volatile components, so XF will be the mole fraction of more volatile component in the feed. XD will be the mole fraction of more volatile component in the distillate or the overhead product, and XB will be the mole fraction of that component in the bottom product. So we can do the total material balance F is equal to D plus B, and we can do the balance for material A or more volatile component. Then we can write in terms of their mole fraction multiplied with their molar flow rate. And we can write our equations either in terms of ratio of D over F or B over F. So it's the ratio of distillate to the feed or bottom product to the feed. So you can write your equations either D over F or B over F. And then you can also perform material balance around the condenser, right? So D over F or B over F gives us information how much distillate that you are recovering with respect to feed, how much bottom product you are recovering with respect to the feed. So you can perform material balance for any component A, you can perform for component B as well, right? Similarly, you can also perform material balance for component B. Normally, what we do that when we make the material balance of more volatile component, we denote our plates as N. But in the case of material balance for any component B or any component which is less volatile or heavy component, so we can denote those part as M. So we denote the parts which are below the feed plate or for the stripping section as M, and the same terminologies that we use for designating the plates. So we can perform the material balance for component B as well, right? So M is used instead of N in order to designate a journal plate in the stripping section, right? So you can perform material balance for A or material balance for component B. Now the question about the operating lines, how we draw the operating lines. Since you have seen that in the gas absorption, normally we have the same section. So we do not have two sections or three sections in the gas absorption. So we have one operating line in most of the cases. But in the case of distillation column, we divide our distillation column into two sections. One section is the rectifying section, and the one section is for stripping section. So it means we will have two operating lines. So we are going to have one operating line for the rectifying section, and we will be having one operating line for the stripping section. So how we can find out the operating line for the rectifying section? So you can find the slope as the ratio of the flow of the liquid to the stream to the vapor stream. So ln over vn plus 1, from this ratio you can calculate the slope, or this dxd over vn plus 1 will give you information about the intercept. And similarly, if you eliminate these vn plus 1, so you can right in terms of the flow rates. So this ln over ln plus d or l over l plus d, it will give you information about the slope of the operating line for the rectifying section, and this dxd over l plus d, it will give you information about the intercept in the equilibrium vapor diagram. Similarly, you can perform the balance, and you can find the operating line for the stripping section as well. Here, Lm over Lm minus b or L over L minus b. So this is based on the bottom product. This will be the slope of the operating line for the stripping section, and this will be the intercept. And the slope of operating line, it is very important that the slope of operating line in the rectifying section will be less than 1, and the slope of operating line for stripping section is always greater than 1, right? So it means like for the rectifying section it will be on the other side, and for the stripping section or it will be on the positive side or more than 1. So this is just to show you that how slope of operating line will work for the rectifying section and slope of the operating line in the stripping section. Before I start giving you step by step that how you can calculate the number of ideal plates and or number of ideal stages in a distillation column, I would like to ask you if you have any questions around the operating lines and or any other question. Otherwise, then I will start with how you can perform the McCabe and Thiele method. Do we have any question? All right, then I'll move with the number of ideal plates that how we can calculate using the McCabe and Thiele method. So I'm going to show you step by step that you perform the McCabe and Thiele method. It's a very easy method, very simple method. There are few things that you need to understand that how you can perform this method. So first, what we do, that why we are learning about the method, it helps us in improving the understanding about the distillation process, the concept of equilibrium stages, and also to develop our basic understanding on thermodynamics of plate or tray distillation. So if we assume that we have this kind of distillation column, and we can denote the terminologies for the stream that are entering or leaving the distillation column. So we can denote D as the molar flow rate of the top product, L is the molar flow rate of the reflux, M is the slope of the line, and then Q is the mole fraction of the liquid in the feed, and some temperatures for feed boiling temperature, dew point, or feed temperature, TF. So first, we have to make certain assumptions. Normally, this method is can be used when we have a system which is binary or the mixture is binary, so it contains two components. The heat of vaporization of two components are equal. Other thermodynamic effects are negligible, like heat of dissolution. We consider the efficiency of the plate is 100%. That's why we call it ideal tray or ideal stage. But practically, fluids do not reach equilibrium on each tray. So the tray efficiencies needs to added in calculation in order to find the actual number of plates. So we calculate the efficiency of the stages, and then we multiply or sorry, we divide with the theoretical plates in order to calculate the actual plates. So normally the number of actual plates are higher than the number of ideal plates or ideal stages. So we do step by step. So first we have on the x-axis, we have lighter component or more volatile component. So the mole fraction of the more volatile component in the liquid phase. And on the y-axis, we have more volatile component or mole fraction of more volatile component in the vapor phase. So we have y-axis, x-axis, we draw a diagonal line. The second thing that we draw our equilibrium curve. Normally we are given with the equilibrium data, so we will have the values of x and we will have value of y. So when we know the value of x and y, so we put our points in this uh, in this graph, and then we can make a consistent equilibrium curve, right? So normally drawing this vapor liquid equilibrium curve, it will be given to you for a certain binary mixture. Now you choose the product feed and the bottom product composition. So let's say that in this kind of example, we have the XD, which is the mole fraction of more volatile component in the top product or in the distillate, let's say is 0.95. Let's say the feed composition is zero point 0.5, so it means XF is around zero point 0.5. And the bottom product, which is XB, so for the bottom product composition, let's say is zero point 0.1. Now there will be a question about the quality of the feed. Either the feed is in the liquid stage, liquid phase, or either the feed in the vapor phase, or either the feed is in equal liquid and vapor phase. So you have to find what is the quality of the feed. If the feed is 100% liquid or saturated liquid, we just draw a vertical line like this. And if the feed is saturated vapor, it means there is no liquid, it's only vapor, so we will have a horizontal line. We will have a 45-degree line, which will be for feed which is equal liquid and equal vapor, right? So this is how you can find the quality of the feed. And you can also calculate the slope of the line by calculating q over q minus 1, right? So let's say that our feed is 45%, not 45, 50% vapor, 50% liquid. So we will have a 45-degree line, right? Now the step 5. Now we need to draw the operating line for the rectifying section, right? So how we can calculate the slope of operating line for the rectifying section? It will be L over D plus L. So if we know the value of L, D plus L, then we can calculate the slope of the rectifying section. And for the stripping section, the point of intersection of the operating line of the rectifying section with the feed line, we take the point and we just join till XB. So you can calculate the slope of stripping section as well, but it's much more easy that you join from the feed line to the XB, right? And then finally, you have to calculate the number of stages. So you start from top until to the bottom. So it means if we need to have a separation where we'll have 0.95 XD and zero point 0.1 XB. So this kind of a system will require around 7 plates or 7 stage, which are ideal, right? So this is how you can count the number of ideal trays or number of ideal plates. But there are variations of parameters, right? And the one variation parameter is the reflux rate. Reflux rate, it's very important because this reflux rate has a direct impact on the number of ideal plates or number of ideal stages. If we have a high reflux ratio, the number of trays required decreases, right? But the problem is if we increase the reflux rate, the number of trays will be decreased, but this increase in efficiency does not come without disadvantages. What will happen if we are handling with the high capacity of the liquid? So it means we will not build a like a high column, but we might need to build a column that is quite wide. So it means wider column will be needed to handle all of the liquid. And in order for a wider column, we might need to have a larger reboiler to make enough vapors to send back through the liquid. So there is always a question that how far we can go with the reflux ratio. Should we have a reflux ratio of 1, reflux ratio of 2, 3, 4, whatever? In theoretically, if you increase the reflux ratio, your number of plates will decrease. And the first question will be, okay, that will be great. That if the number of ideal stages are smaller, it means we might need to build a shorter distillation column, and the cost of building a shorter column will be small. So why not to increase the rate of the reflux? But this idea will increase the dimensions or the diameter of the column, right? So there are certain disadvantages. But if you keep on increasing the reflux rate, you will not achieve high capacity of the distillate or high capacity or high volumes of the overhead product, which is your main purpose that you would like to produce a overhead product or a bottom product, right? So it's very important that you understand when you are designing a particular distillation column, Either you would like to have a higher reflux ratio or a lower reflux ratio, or what could be the optimum reflux ratio, right? So normally we design our distillation column in a way that we have a certain optimal values for the reflux rate or reflux ratio. So separation efficiency by distillation, it depends on the reflux ratio. So higher the reflux ratio, it means lesser number of required plates will increase, and it will be vice versa. And the R will be changing with respect to slope of the operating line of for the rectifying section. And you can also calculate the slope of the rectifying section using the reflux ratio. So if in the problem it is given the reflux ratio either 1, 2, 3, 4, so you can calculate the slope of operating line for the rectifying section by just having a ratio of R over R plus 1. So this is how you can also calculate the operating line for the rectifying section. So there is one question. If we increase the reflux ratio, when R increases, what will happen? Our slope of operating line for the rectifying section will become steeper. It means you will have a slower intercept, right? And if we decrease the value of R, if we decrease the value of reflux ratio, what will happen? The slope will also decrease. And when the slope decreases, it means the intercept, which is xd over r plus 1, it increases and it rotates upwards. But there will be certain consequences. If we have value of r decreases and the operating line moves closer to the equilibrium curve, right? So it means the driving force will be smaller. If you remember, I told you yesterday, the distance between the operating line and the equilibrium line gives us information about the driving forces. There should be certain driving forces in order to achieve mass transfer. But if the operating line keep on moving closer to the equilibrium, what will happen? The driving force will be reduced and number of stages will be higher, right? So we achieve a point that is the intersection point of the operating line with the equilibrium curve. And normally this point is called the pinch point, right? So at pinch point, what will happen? The driving force for the mass transfer is zero. So it's no driving force. There will be no mass transfer, right? So it's very important that we deal with reflux ratio in a way that it should not go very much closer to the equilibrium curve or should not go too far from the equilibrium curve. So we have an optimal value of the reflux ratio. So there is an important thing that when we use McCabe and Thiele method in order to calculate the number of ideal stages or number of ideal plates, so it's very important in order to calculate the actual number of plates that will be required. So theoretically it is fine. You can calculate that, okay, we will require 10 plates, 11 plates, 20 plates, theoretically. But when you design your distillation column for a real purpose, for a practical application, we have to consider the efficiency of the tray, efficiency of the stage. That's why we include efficiencies. So normally we have distillation stage that operates under conditions which are apart from the equilibrium. So it means we will require a little bit more stages as compared to the ideal plates or ideal stages. And this is a measure of efficiency that we use to compare the performance of an actual stage to an equilibrium stage. So overall efficiency is equal to number of theoretical plates or number of equilibrium plates, number of ideal stages divided by the number of actual plates will be required. So for example, if we know the efficiency of the stages and we need to calculate the number of actual stages, so we put n actual here and we divide the theoretical number of plates with the efficiency. So we will have the number of actual plates will be required. So it will be, since the efficiency is less than 1 or less than 100%, so it means the number of actual plates will be higher than the number of equilibrium stages. Right. So that was about the efficiency. I have added some videos on like some animations around the distillation column, the Murphy efficiency of the stages. I have also added some basic videos on distillation column for your better understanding. So I hope that you have watched those videos, or if you have not watched them, then please do it. It will help your understanding, because normally what happens that when we see an actual distillation column, like a cross section of the distillation column, we understand things much more easily. We can relate to that phenomena, that how vapors are moving upwards, how liquid is moving downwards, what is happening on each stage, how the vapor and liquid are going to be mixed, how they are interacting with each other, right? How the mass transfer is happening. So it is very important that you watch those videos in order to improve your understanding about the distillation process. I have added some recommended problems for the distillation in the canvas, and I have also maybe I can show you. Mm, So I have recommended some problems for the distillation. So there are two problems. One problem is that if you are asked to design a continuous distillation column in order to separate 10,000 kilogram per hour of a liquid mixture, we know that the liquid mixture that contains 40 mole percent of methanol and 60 mole percent of water in the feed. So the overhead 97 mole percent of methanol, and the bottom product contains 98 mole percent of water. So it means it will be 2% of methanol in the bottom product. If you can assume a mole reflux ratio of 3 and equilibrium data is given, then you can perform a material balance in order to calculate the how much overhead product or distillate you can obtain per hour, how you calculate the number of ideal plates, and you can find out what will be the location of feed plate if the feed is at bubble point. And similarly, I have also another question where we know the feed plate, which is 8, and then you have to calculate um what are you going to calculate? Mhm. What is the question? I think in this you also need to calculate number of plates, right? How many how many theoretical plates a column must have. So you have to calculate the number of theoretical plates if these are the conditions, and if the feed is introduced at the plate number 8. So there are two recommended problems, and they are very easy. You just have to remember that how you can perform the McCabe and Thiel method. And it is very important that you go through the text in the book about the distillation in order for you to understand that why reflux ratio is important. There are so many questions in distillation that why it is important to know the efficiencies of stages, what are different types of efficiency of stages, right? So there are so many questions, what kind of packing that we can use, what kind of plate column that we can use, what sieve tray that we can use. So I suggest that you read the chapter from the book, and also you can go through with my PowerPoints and solve these problems, right? And then I will add an home exam or home assignment for distillation as well in a couple of days, and then it will have a deadline, which will be after the humidification deadline, right? So I think we are done for today. And I just would like to mention that there will be no home assignment for yesterday's discussion, that is on equilibrium stage operation, because that discussion is very important for you to understand about the equilibrium and how we designate the plate numbers, how we designate the streams within the cascade systems, right? So I would like to ask you that if you have any question.
Is the equilibrium curve always like as you said constant like over the mole fractions?
If I understand you correctly, you mean to say if it will have like a linear curve or it is non-linear curve, right? Is it your
Yeah, like the first example, so that it's sort of like a yeah, parabolic shape over the first one that you showed.
yeah? It can be very consistent, but it can be a little bit inconsistent. It's normally for non-ideal systems where when the equilibrium curve is not like a very equal parabolic shape, but it can be a little bit wavy. That's one I showed you in the pictures for VLE diagrams. So it can be at different, but you can use the equilibrium data, and then you can use the equilibrium data to produce the equilibrium curve, and then you can calculate your stages accordingly. So it can, but you will not have problems where you will achieve azeotropic point, because in this course we are not dealing with azeotropic distillation in detail. So you will have a consistent equilibrium curve, or maybe I can show you for those recommended problems how the equilibrium curve should look like. Let's see. So for the first so for the like this first curve, if you look at, it is not very much consistent. It is going a little bit up here, up here, up here, and from that part it is going to be a little bit stable. So it's not 100% consistent, it's not 100% parabolic, but it's parabolic, but in a way that initially it is going till this point, it's very steep, but then it's going to be a little bit horizontal, moving towards more horizontal. So it will look like this for the first system. And for the second system, so this is like for the second problem, it looks like it is very much consistent. So it's not like it has a quite similar slope, or the slope of the equilibrium curve is not changing that much. So it's going very nicely from 0 to 1, right? So I would like to ask you that if you have any more questions. So if we do not have any more question, then I will say goodbye. But I'm missing. There is one question about assignment on humidification. How deep should I go in the subject? So if you find not many information from the book, you can always search the internet. You can find as much as information possible. You can consult the book, you can consult the book chapter or many different books, because normally I refer to many different books in order to understand or develop my knowledge or develop my understanding for that particular separation technology. So it's up to you how deep should you need to go into the subject. But the prerequisite or the mandatory part is that you cover all those aspects which I have included in my discussion. So all the small topics that I cover in my PowerPoint, you have to learn about it, you have to think about it, you should know what we have discussed the while I am going to have a discussion, or while I put the PowerPoint in the canvas. So those topics should be covered. But if you want, you can go as much as detail, whatever you like, right? But in reality, practically, it is very important that you should cover all the small topics that I have covered in my PowerPoint, because all these PowerPoints are made on the basis of the total learning outcomes of this course, right? And we have to achieve all the learning outcomes in the course, right? So you have to work with all the important points for e-separation technology that I cover in the PowerPoint, that is equivalent to what we have in the learning outcomes of the course. But if you want, you can go as much as deeper as you would like. Right. So I would like to ask once again if you have any questions. Otherwise, then I'll say goodbye, and then we are going to meet next time, and we will discuss our final separation technology, which is drying. And drying is very important for us to understand. Right. So if you have, I will try to upload the video on the drawing and the PowerPoint as soon as possible. So I again suggest that whenever we meet next time, it's important that you can watch the video lecture and also the PowerPoint in order to have a more productive or like more productive discussion in our Zoom meetings. Right. So if you find any questions, you can write me an email, or if you have any questions now, you can ask. Otherwise, then I will say goodbye and wish you a good day.